Welcome everyone to the Net Zero Energy Building Knowledge Series. This is a platform that brings industry experts to share their expertise and knowledge and also showcase projects, products, technology, and even ideas to grow engagement for building energy efficiency and net zero energy buildings in India. This is an initiative supported by USAID under the Market Integration and Transformation for Energy Efficiency. You can know more about the program on our website, metri.etsglobal.com. I'm Deepa. I am an architect and a green building consultant, and I will be the session moderator today. Today we have a very interesting topic. We're going to talk about an interesting net zero energy retrofit for both ASHRAE, for the new ASHRAE headquarters in Atlanta in the US. Now, all of us know that, all of us know here about ASHRAE. And yes, this is a demonstration project as you might expect it to be. But what's interesting here is that ASHRAE decided to develop a project that is a model of what is scalable, economically feasible, and replicable by an average building owner to achieve net zero. And that to me was a very interesting approach when you literally had all the options open to you. Talking more about this project today is Shreshth Nagpal, expert speaker for today. He's joining us from New York. It's 9 a.m. for him over there. And he is a principal at the Integral Group that is providing engineering design and analytic services for this project. Shreshth's professional focus over the past 15 years has been to understand and model building performance that results from the interaction between envelope configuration, climate context, functional requirements, conditioning systems, and occupant behavior. More recently, his doctoral research focused on developing automated workflows to construct living urban energy models that are designed to systematically explore future energy scenarios and identify areas of maximum potential savings. Shreshth especially enjoys working on projects with a focus on designing with passive strategies for thermal and visual comfort, and has completed specialized building physics analysis to help inform design decisions of several award-winning projects that represent a broad spectrum of type, scale, climate, and performance goals. I welcome you, Shreshth, to the webinar today. And I'm just transferring the controls to you, and you can start presenting.
All right.
Okay.
Thank you, Deepa. So you're able to see my screen, and hello everybody, and thanks for joining the webinar. Couple of things I'm going to do as advised. I'm going to turn off my webcam now, so hello everyone, but it takes a lot of bandwidth from what I understand. That's that. Okay, let's try and make this work. Okay. So thanks again, Deepa. And as Deepa mentioned, my job today is to talk to you all about a very cool project that we've been working on for the last few months. It's the renovation of global headquarters for ASHRAE. Everybody here knows ASHRAE. Everybody here knows what a global headquarters is. I will talk about our contribution, what the design focus has been, and what the design is going to finally be able to achieve. So the way this presentation, this talk for the next 30-40 minutes is going to be structured is I'll try and introduce myself, not just myself, but the design team. I'll introduce the project, what the challenges and the visions for the project were, and then a very straightforward process of how you approach taking design decisions for a high aspiration, high performance project. And I'll talk about each of the different aspects of design that we looked into, that we discussed with the architects, with the client, and then what decisions we took so that we reached where we reached. So that will end up with a summary, and then we'll open up for questions. So let's see. Let's start with the introduction. I should, at the outset, mention that this was a very interesting project from the very beginning, because the client, they are ASHRAE, they knew that engineers, which is the firm that I represent, have to be an integral part, and our name is Integral, of the design team. So it was very clear from the outset that the design team leadership would be a joint effort between, there are two architecture firms involved, Hauser Walker Architecture, the architect of record, McLennan Design, who are the design architects and also the lead sustainability designers, and then Integral Group, which is MEP, fire protection, and we are doing design analytics. So if you see on the screen somewhere on the right, along the entire design team, there are many people who've contributed significantly. I am somewhere in there, listed under the energy modeling category. So that was the team that was formed. This was a competition project. We were the winning team, and this is what was submitted as part of our program. So within this team of 3 joint leaders, the Integral Group, which is, like I said, I represent, say that we are a engineering firm. MEP is our primary focus, but we are very strongly committed to decarbonization and resilience in the built environment. That has been our thing, that has been our focus, that has driven the growth of the company, the projects that we seek, the projects that we go after. And what you see on the slide is, so what's in blue is what I edited very recently, because the background graphic is a few years old. We have several offices, a huge presence across the world. We have over 100 net zero energy projects either built or on the design board. Similarly, several LEED Platinum projects and some passive house projects, living building challenge projects. So the point that I'm trying to make is, as an engineering firm, we have been in the middle of this whole high performance movement. We've been leading this movement, and we've been on top of it. Within that firm, the practice that I represent is called Design Analytics. We are based out of New York, and the whole point of this practice is we are a group of specialized individuals with deep knowledge, and the idea is to support all practices across the company, across the world. We call those broad knowledge practices like engineering or even policy or health and wellness. But the idea is, if any quantified decisions need to be made, or if any design decisions need to be informed by analysis, that's the job that we do. So within this design analytics practice, the focus of today's talk is, of course, energy. And this is the group that has done a lot of work on this project. Mike Esposito, the first image on the left has been the key player in all of the analysis. I'm going to present a lot of his work today. And of course, the second image from the left is me, and I am talking to you, presenting most of Mike's work. So which brings us to talk about the project a little bit, now that you know me and who I represent. So this is ASHRAE. They needed to move out of their current place and look for themselves a new headquarters. They purchased an existing mid-century building that was built in 1970s. It's about 67,000 square foot. It's near Atlanta, Georgia. That's where the current headquarters, that's where they currently run out of as well. The challenge for the project was that, this being an organization that everybody looks up to, they needed to do something to their building. That's not only a demonstration from the perspective of high performance, but also a demonstration project for anybody who's trying to do something similar. So they did not want to present all the cutting edge, completely unfeasible strategies that is well within their purview, because they're ASHRAE, they can do anything in their project, but they wanted to do a retrofit that is replicable, that anybody else can implement in their building within cost constraints, budget and time constraints, and still achieve a net zero performance, which becomes the next challenge. This is defined as mission critical, that the project after renovation has to be net zero. There is no two ways about it. And along with just being net zero, they also wanted to put a cap on what the energy use intensity was going to be before the renewable energy starts contributing, just so it doesn't become a narrative where all that you ended up doing was designing an inefficient, crappy building and then just make up for all of it using PV. They have a large site. You'll see in a site plan in a minute, but the idea was not to fill up their site with renewable energy and offset whatever energy they consume. The idea was also to design a building that's high performance and energy efficient. So the vision of the project, which follows on from the challenges when they set out for themselves this project, was it has to be a showcase of latest technology. Again, they wanted it to be a place where engineers or all members or anybody who's associated with the built environment can stop by and see how an efficient building is supposed to be designed and operated. The project was, of course, going to be superior efficiency, as we discussed in the previous slide, and provide a healthy and comfortable environment. Again, things that ASHRAE is deeply passionate about, which follows on to say that this project has to represent the values: sustainability, high performance, comfortable environment, occupant health, that, of course, we all know ASHRAE has long held, and then, of course, the zero carbon footprint and zero net energy operation. So when the project started, the design team was given these challenges and this vision, and the first thing that we sat down and decided, and it's part of the competition that we won, that this project has to follow first principles. Even though this is a retrofit, so we are already starting on the right foot. We are not expending a lot of embodied energy in constructing something right out of the ground. We are taking an existing building. A lot of embodied energy has already gone into it. Now let's use first principles to design something that completely and entirely responds to the climate and the place, which means the massing is not so much in our control because it's an existing building, but we can at least configure our envelope to respond to different orientations. And then all the regular things. There's no reason, given their site, given their context, given the exposure that they have, that they should be relying on electric lighting at all. This space, even though the building configuration right now does not lend itself to very narrow floor plates and there is not enough daylight, but can we retrofit to make sure that most of the occupied hours can be completely daylight, but there is minimal reliance on electric lighting. Thermal comfort follows visual comfort, and wanted to make sure that as much as possible, passive strategies alone or responding to the outside environment alone can meet comfort criteria. And we want to use natural ventilation, we want to use expanded comfort range, and then we want to follow it with low energy systems. Whatever loads, whatever comfort criteria we cannot meet entirely by passive strategies, we wanted to make sure we are using the right systems, the most efficient systems, controlled in the most optimal way to provide for occupant comfort. So the first thing we do, as anybody does when they're trying to design a net zero energy building, we try to establish for ourselves exactly where are we starting from. So ASHRAE had set for themselves very stringent targets about what the lighting power would be in the building, what the equipment or plug load power would be in the building, and what we found was that if you were starting right from scratch, if this was any other building where the owner was not cognizant about reducing their own operating or functional or programmatic loads, the building would be somewhere around 36 kBTU per square foot per year energy use intensity. But because ASHRAE was itself a motivated client, they knew what they were doing and they have set programmatic targets for themselves. They were already at a very significantly better starting point based on where they are right now. If they just moved into this building and updated it to minimum ASHRAE requirements and made sure that the lighting power densities and the equipment bar densities match the project requirements that they have set for themselves, they would be at about a 30 EGY. Now, what the slide also shows is the target that they have set for themselves, which was 21.4. So at this stage, the project design hasn't even started. We haven't thought about what we would do. All that we know is we are at about 30. We need to be at about 21.4, and then we'll figure out how to offset that through renewable energy. Whether we can or cannot is up for discussion or up for investigation, but we'll get to that. So that sets up the starting point, at which point we start to decide to develop a baseline, right? So what a baseline does is you, with the energy model that you already have, and this I should just mention is a very standard process of almost all projects that we start working on, just to understand our starting point. What you see as the series of graphs on this screen are sensitivity analysis for different envelope measures. the impact of incremental improvement on any envelope parameter. The top left chart, for example, is wall hour values. The next one is roof hour values. If you improve these parameters one step at a time, what's the relative impact? What's the delta? What's the change on energy intensity of the project if these things were to improve? What that tells you is a point where you reach diminishing returns and where you recommend that there is not enough bang for the buck to upgrade these things anymore. So this is what we recommend. What you see on the graph is, I think, solid blue dots, which were the baseline values, which ASHRAE recommended or ASHRAE prescribed based on ASHRAE standard 90.1 for this climate zone. And the lighter, larger blue dots, which is what we recommended for the project based on our understanding of the program, the operation, the building form, the building mapping, what would be most optimal for this project, where we think we should strive to design to at least these values if you are to achieve optimal performance. So just to wrap up this slide, the last bullet point on the slide is what we're recommending is you should have R17 walls, which is not very aggressive. Just to keep in mind, this is Atlanta, Georgia. This is ASHRAE Climate Zone 3, so it's not moderate like California or some other places, but it's also not as hot or not as cold as Minneapolis, or not that extreme of a climate. So R17 in this case does fit that. R35 groups, you saw the building mapping a little bit earlier. It's just 2 stories. The roof plays a significant role in heat transfer, and insulating the roof becomes important. And then the overall assembly of U values. And these are all IP units, 2.4 BTU per hour square foot degree Fahrenheit. So that's the assembly U values that we are recommending. Now the question is that we need to, of course, be able to design to these values, but we know as a starting point, if we are able to achieve these performance parameters from our construction, from our detailing, from our design, we should be performing okay from an envelope perspective. The next step that happens is, and this is supposed to be interactive, but because this is a static presentation, some of you or many of you would have seen a chart or a graphic like this before. Essentially, this is a parallel coordinates graph. It takes a step further from the previous sensitivity analysis. We prepare for architects and engineers and ourselves, the design team generally, as a decision-making process. All the vertical axes on the left, except the rightmost, represent the same envelope parameters that were evaluated earlier. And the rightmost axis is the energy use intensity that results from any combination of these parameters that you can actually pick and choose in this interactive graph. So the idea is, if you are thinking you want to compromise on a certain parameter or make a certain parameter more aggressive, you can fix it at that and see what the impact of choosing another value for another parameter would be. So all of this helps appreciate and understand what might go wrong or what might result in the maximum savings if you were to choose a slight improvement or a slight degradation in a specific parameter. The other cool part that I should mention that we started doing recently is to produce, anybody who's done energy analysis, energy modeling in the past, they know that setting up these hundreds of thousands of runs, or at least tens of thousands of runs to model every single permutation and combination, while possible, is not the most fun thing to do and thinkful after a certain point. What we've started doing is we use surrogate modeling, which is basically a statistical interpolation method to generate results for a lot of combinations that we don't actually model using energy models. So the graph that you're seeing on the right, the dark line is a result of an actual energy model, and the way it's selected right now, it's only showing one. I think you would have run about 100 simulations, and then we would have generated results for statistically generated results for about 4,000 or 5,000 other simulations using surrogate modeling techniques. Those are all the light blue lines, but it gives a full design space exploration opportunity, and the team can look into different options and select what they want. The next thing that follows from this is essentially, this is the real baseline that we set for ourselves before we dive deeper into the design strategies. What this is showing you is, this is your starting point on the extreme left. And I should mention, this is going to be an all-electric project, and I'm sure many of you have started experiencing that or this has become a standard part of conversations right now. The future is going to be all electric, because the only way you can get to carbon neutrality or eliminate any fossil fuel usage on site or on your building is if you're not consuming any fossil. Now, cost is still a completely different argument altogether. Here in the US, where natural gas is much cheaper than electricity in most regions, but any client or any design team who knows that they're designing for the future are cognizant of the fact that they have to start eliminating any fossil fuel usage. So what you see on the extreme left of this graphic is the total energy use intensity, which is all electric, that the project will consume. You would remember at the end of the last section, I showed based on just ASHRAE requirements, we were at about 30 EUI. Now we did that analysis in the previous slides about trying to find the optimal envelope, and that if you start using recommended envelope properties, that EUI drops down to about 25, which is all electric. The critical thing here is to understand where that 25 EUI of energy is flowing. What are the different end users? Again, for all of those who've done energy analysis and energy models in the past, they're very familiar with the second vertical axis here, which is the energy end use. We always present our energy use distribution or energy use characterization based on the different end users that we know the building will consume. Where it starts to get interesting is to understand where is heating coming from and where is cooling coming from. What are the different heat loss and heat gain components? What are the different passive things that are contributing to free heating and free cooling? What this does is it starts developing an appreciation for what are the things that are important for the project. In this case, for example, you see that heat loss through windows and solar gains, again through windows, are the largest heating and cooling components respectively, which basically means that if you want to further reduce your cooling and heating energy, those are the things that you need to target. Maybe a smaller window to wall ratio, maybe optimized shading, maybe improve the U values of windows further. But one way or the other, you know what strategies will give you or have the potential to offer you further savings, and what strategies just might not get you any returns, even if you spend a lot of money on upgrading those. So with that in mind, as I just explained, the moved from 36, which could have been a standard project starting point, to 30, to where ASHRAE, the client itself, this is kudos to the client who knew what they were doing, brought it down to 30, and then a very simple early stage energy analysis, an energy model that optimizes or recommends what the optimal construction value should be, brings it down to 25. So now on the face of it, well, you can tell that the chart is very long horizontally, so there is a long way to go, but we are very close to the target which ASHRAE set for themselves here at 25, and we need to hit 21.4. So far it looks that it's easy. So we should get there soon enough. But this is where this is in fact where the design process actually starts. All of this is just a preamble to even sitting down at the drawing board. All of this work is completed to understand what we are up against, what we are dealing with. So now we can start thinking about design strategies, understand the context, climb it in place to see what else can be done. Which brings us to the next point, which is, as we all understand, the first design stage process to understand what the climate, the context, the site for the project is. Right. So the mapping, unfortunately for us, because it's an existing building, is pretty much fixed. Like I said earlier, what we can still do is make sure that different orientations, different envelope portions respond reasonably to orientation, to solar geometry, to solar impact, radiation, incident radiation. What these charts are showing you, this is breakdown of summer on the top and winter at the bottom. The amount of radiation, the magnitude of radiation that's incident on each facade based on their orientation during the different seasons. Right? So as we all understand, the goal here is to minimize summer radiation and maximize winter time. Again, as most of us know from first principles, in doing this over and over again, chart essentially is reinforcing what we already know, that east and west are to be avoided because they get massive amounts of radiation in the summers, and it's the most difficult solar radiation to control because of low solar angles. And those same orientations don't receive anything, and this is specific to Atlanta, of course, for this climate. they don't receive any solar radiation during the winter. So having any fenestration on the east and west faces is only going to hurt you without any significant passive solar gains benefit. On the other hand, north, of course, is a good orientation for solar control, and south can be easily controlled. So the idea is try and minimize fenestration or window areas on the east and west, and if you want to increase it for purposes of daylight and others, you can target north and south orientations. I think based on simply the climate analysis or the solar radiation analysis, we said the window to wall ratios term that everybody is familiar with, I would imagine is not more than 30 to 40%. Restrict to 30% in east and west, and restrict yourself to 40% on the north and south. This is simply based on solar orientation. The next thing is to start looking at psychrometric data. I should clarify, it'll load in a second. I think the charts that you're seeing on the screen are not just plots of outside air conditions as we typically start doing. These are indoor operative temperatures that are result from an energy model that we've already built, that you saw we've already produced for the project. What this is showing you is natural ventilation potential and what happens, how many hours in the year can be brought under comfort conditions depending on how you define for yourself comfort criteria and how effective you design natural ventilation. The key strategies being, what if you only open your windows and allow for natural ventilation during the daytime? And then if you want to advance it further, what happens if you start relying on night purge and charge your thermal mass at night so that the radiant field changes and people are more comfortable during the hours of, at least the beginning hours of occupancy. So what you see is that if there was no natural ventilation, that's the top left chart, the number of hours that fall within the comfort range, or these, again, repeat, these are indoor operative temperatures. The temperatures, so these account for the internal heat gains, envelope losses, the operating hours and everything else. The number of hours that would be comfortable if the space was not conditioned and not naturally ventilated would be less than 20%. If you start making the natural ventilation strategies more effective, incrementally, the number of hours that can be comfortable increase from 20 to 30 to 40 to almost 56%. So that's a significant number of hours that you can be comfortable without reliance on any active systems. This is another important part of climate analysis because it tells you that it's really important to design for natural ventilation in this climate. Now, how you design for it is a different ballgame altogether. You want to make sure that there is enough inlet area, outlet area, and cross ventilation and opportunities, and your internal layouts are not obstructing. But the idea is that there is enough potential to gain or to reduce your energy if you design a natural ventilation scheme really well. And finally, as part of the climate analysis and understanding the context, you look at what the renewable energy potential of this follows the solar radiation study that I presented earlier. The idea is, because this is supposed to be an efficient building and we don't want to go down that route where we let our building consume whatever it consumes and then just fill up our site with photovoltaic modules, the idea was to understand how much the roof itself can generate so that it becomes a true net zero building, so that we know that within our building footprint, whatever we consume, we can offset. And based on the optimal orientation, based on what we thought was the other mechanical equipment, or at this stage, the skylights to improve daylight would go on the roof, the amount of area that we are left with, we figured based on our initial calculations that we can offset anywhere between 15 to 17 BUI. So at this point, we know that if this needs to be a true net zero energy building, we need to make sure we know that we can only offset about 17 kBTU per square foot per year from the roof area itself. So if I go on to the next slide, the idea is that what used to be our previous target that the clients have set for us at 21.4 is no longer valid, because if you're trying to design a true net zero building, the net zero energy target reduces to about 17. So the goal at this point becomes that we were at 25 before doing anything, or to justify the right constructions and the ASHRAE project requirements. we need to take that 25 down to 17 somehow, which means we need to start focusing on doing all the right things as much as we can. So the first thing that does is start looking at the program. What is the building going to be used for? What are the different spaces supposed to be? What are the requirements of all of these spaces? So starting to work with the architects and the interior layout of the space. So this is an office building. That is the global headquarters for ASHRAE, which basically means it's predominantly an office space, but there are some event spaces because they expect industry people and members to show up for events. And then there are conference rooms and all the other regular things that you would expect in a space like. Now, there are several different ways in which the spaces can be organized. The three massing or the three layout organizations that you see on the screen, the names that the design team gave were mixed, stratified, and stacked. But the idea was if you laid out the different spaces scattered over the entire floor plate, it gives a good, what they call inter-department workflow, because if you want to go to a conference room, you just step out of your office and you have a conference room, for instance. And the second one is slightly different because it combines all spaces with similar requirements, thermal perspective or daylight perspective together. And the third one was slightly different. The third one was actually eliminated very early on in the design process. But if you just look at A and B, the idea is the scheme B affords or allows us to condition the spaces more optimally, because all spaces that can have an expanded comfort criteria, for example, are together. The spaces that have strict conditioning criteria can be together, which means they can be more efficiently served by the HVAC systems. And similarly, the spaces that have a similar daylight requirement are clubbed together in the same place where they have those daylight qualities. So the program organization itself can start influencing how the spaces are utilized from a thermal comfort and from a visual comfort perspective. So the stratified scheme B was picked eventually because of the obvious merits of how it would respond or manifest itself to energy efficiency. The second thing was the ATRIUM, and if you remember looking at the scheme earlier, the building image that I showed earlier, there is this huge atrium right in the center, which is completely glazed, completely not designed for energy efficiency. It was a greenhouse. In fact, I read somewhere in the design team narrative that is an example of exactly what not to do. The idea was to change this atrium with an opaque roof so that it stops being a greenhouse and design it with enough shading and solar control so that this atrium can become an interstitial space so that it does not need to be even conditioned anymore. And it can become a totally passively tempered space as a transition between the two building blocks, but you stop conditioning it, heating it, or cooling it anymore. And then, of course, the whole notion of expanded comfort range. As designers, we are very aware of the fact that perceived thermal comfort is a result of several different factors. Air movement around you, with ceiling fans, or the radiant field around you, because that affects your operative temperature. So the idea was, and this is again in Fahrenheit, so a thermostat set point of 75 degrees, what you perceive there as a mixed air space without any radiant systems, with still air conditions, almost translates to very high temperatures if you're making sure that your air movement and radiant field are optimized for. And you'll see the sketch again as it shows up in the coming slides. But the idea is, with all of these things, making sure that our program layout is done correctly and the comfort criteria is defined correctly, we reduced our EUI by another 3 units, and we are close to 22 EUI. So that brings us to a point where we looked at construction, we have looked at program organization, and we've looked at comfort criteria. Which brings us next to sometimes the most critical aspect of a project, which is further details. Beyond constructions, what we want to do to the envelope. So we've already defined for ourselves what the different window to wall ratios should be, what the different shading configurations should be. The design team spent a lot of time drawing out what the different configurations could be to achieve those window to wall ratios. One thing that is very important to understand, so these are punched openings. These are going to significantly reduce the window to wall ratio of what the project already had, which was about 70-75%. So the idea was, because this was to be a demonstrable, replicable process, which basically means it had to come under budget and it had to be feasible. The design team was always trying to make sure that the windows, the new windows, can fit within the existing precast panel configuration. The idea was not to rip out the entire facade and start doing it all over again. The idea was to do minimal interventions so that it's cheap, it's inexpensive, and it's easily done. So using the same configuration as the existing building or within the bounds of the modularity of existing envelope configuration, we design different things in which we can achieve the window to wall ratios, and the red lines that you see in the graphics below are the shading configuration. So east and west require both horizontal and vertical shades. South only requires horizontal shades for optimal solar control. So this is where we ended up for window configuration. So it's very simple. It doesn't look glamorous a lot. It's not fully glazed. It's very small punched windows. So it has a lot of merit to it. It is really inexpensive to do given the bounds of where we are currently. It hits the window to wall ratio, and these are of course optimized for daylight distribution. So it was not that we consolidated the entire 30% together. We distributed it to make sure that daylight distribution within the spaces was fine. The next thing, talking about daylight, was the skylights. I mentioned earlier, relatively deep floor plates. It was not easy to allow for daylight penetration deeper into the floor plates just by perimeter windows. So we started talking about how we start punching openings in the roof to make sure we get enough daylight everywhere there are workstations. So what you see on the top is the initial sketches and the optimal places of skylights based on where we knew the workstations would be. And the scheme was the skylights would be right above the circulation areas, and the workstations will be around the skylights. The workstations will have drop ceilings because that's where we plan to have radiant panels to improve the thermal comfort. And in any case, skylights right above workstations would result in glare and could potentially result in glare and visual discomfort or too bright situations. So based on that, the graphic on the left and the right, you see what the baseline condition was, the amount of daylight that the percentage of regularly occupied workspaces that got useful daylight. We improved it from 36% to a much higher number based on the final skylight configuration that was decided. And the last thing to do with envelope was again existing walls, but you're going to add insulation to these to hit the target values, and we did detailed thermal analysis to make sure that we are eliminating any thermal bridges. What's interesting in the two graphics here is if the same amount of insulation you were to add to the interior of the wall assembly against adding a continuous insulation on the outside of the wall assembly, very different results. So very similar costs from a materiality perspective. The details get difficult if you're trying to do external insulation, of course, but it's significant difference between what you achieve from an overall performance. R10 on the left to R24 on the right. So first we are going to stick with the right scheme because that also meets the minimum criteria that we have set. But studies like these help inform that on the face of it, it's the same thickness of insulation, it's the same material, but because of thermal bridges and because of heat loss or increased heat gains through where the slab meets the edge, if the insulation is not continuous, you can seriously degrade the overall performance of the assembly. So more thermal analysis, and finally, if we did all of this envelope configuration, the windows design as I showed you, the shades implemented where they were needed to be, and envelope constructions, the wall insulation values that we just spoke about the details, we reduced our EUI to about 19. So the difference between recommended constructions 25 and this step is that was just a starting criteria of what we wanted to achieve. This is now based on actual design details. This is what we know we are going to do, right? And then I think at this point we wanted to take a break, and I'll let Deepa decide what we wanted to do.
Yeah. Thank you, Shreshth. That was very interesting and very clear in how you went about the design process and all the different analysis. It's particularly, you would have done so much of work, and then condensing everything back into a few slides is really challenging. So I think we should have right now a little quiz, and just to reinforce if everybody understood what have been covered so far, and to have some interaction with the attendees. So we have a little quiz here, and it'll be up on the screen now. Yes, so everybody can see the question on your screen, and you can put in a vote by clicking on it, so we get the responses. Question is, the existing building was selected for its favorable climate responsive orientation. Yes, no, or not sure. Make sure you give in your votes, even if you're not sure, so we know whether we should discuss this or we shouldn't, and whether everyone has followed through or not. The votes are coming in. I'll wait for a couple more seconds, and then we can start. Okay, so it's interesting. 53% saying yes, and 35 are saying no, and the rest are not sure. So I thought this one would be like completely leaning on to one side, but it's not the case. So answer is, well, as far as I understand, it was not really selected for its favorable climate responsive orientation. So answer is no, because clearly the building didn't have a favorable orientation, right, Shreshth? So
yes, I mean the building had the orientation that it had. We had no role in being able to optimize where it was facing. All that we could do was make sure the envelope responded to orientation. So it seems like a trick question. But I understand that people are split.
Yeah. So, well, most of them are saying yes, so we should talk about this. And why was this building even selected? What was the criteria? Did the client select between a few buildings, or is this the only option they had?
It's a good question. So I should clarify that we became part of the design team after ASHRAE had already picked the building. So as a design team, we did not have much role to play on what they should pick. Now that said, a little bit of background that I know, they did their due diligence. They knew what they were looking for. I think I read somewhere that finding a building for your headquarters is very similar to trying to find a house for yourself. There are few things that need to be met from a space requirements, from a location requirements, that it's connected to all amenities, that it has public transportation, and the fact that I think they knew that they're going to retrofit an existing building because of the whole embodied carbon and embodied energy portion. So within the geographic region that they wanted to be at, within the space constraints that they wanted to meet for yourself, and within the community connectivity that they wanted for themselves, I guess this project trumped what they wanted to have.
Okay, that's interesting. I would imagine there is more effort in retrofitting a building. That was my general understanding. Than it's just easier to build something ground up, and net zero or whatever target you set for is just easier to select and just build something from scratch rather than try to do little renovations, etc., breaking and making new things. But I guess you are setting up a model which is showing how cost effective this is. So that I think was really made a very interesting case for this project to be talked about on this webinar.
Absolutely, that's a very fair point. If we were to build something ground up, of course the building would have narrower floor plate. It would not look like this. Of course, the building would be oriented differently. Of course, the building would not have the atrium that you see on the screen right now with the fully glass ceiling. It would not have the 70% window to wall ratio that you see right now. So there are a lot of things that could have been done differently within the same programmatic requirements. It's absolutely more challenging to start from a base that is already not designed too well and try to make it into something that is high performance than to start from first principles and build something ground up.
Right. Then we have one more. We have 15 more minutes, so I'd like to skip the second question and let's.
There's only a couple of slides left. So we spoke about envelope, we spoke about program. The next thing is that I represent an engineering firm, so I better talk about systems a little bit because they also have a role to contribute. So far what we've discussed is we've managed to reduce the loads. We've designed our envelope to optimal insulation levels. We configured our fenestration properly. We designed the shades. We chose our glass based on what we know works best. We thought about airtight construction and infiltration. We did all of those studies earlier. We maximized daylight. So we come to a point where we have maximized comfort conditions, visual and thermal, for as many hours as possible through passive strategy interventions, through envelope, through natural ventilation, through daylighting, and all the good things. So this is a section that we drew as a starting point of where the systems start coming in. So the diagram shows, the sketch shows all the interventions that have gone into the existing building to make sure we achieve as much reduction of loads as possible. Next is start thinking about, so what's the optimal way to start conditioning these spaces? And I mentioned this briefly when I was talking about extended comfort range. We knew that people are a lot more comfortable when there is sufficient air movement around. The convection coefficient against your skin changes completely, and it enhances your comfort perception. So we knew that ceiling fans are going to play a big role. We also know that when you, so that's the starting point. This can work very well with natural ventilation. So we know we are going to design a mixed mode system where there are operable windows, where there is a natural ventilation, and we started looking at whether that atrium that you saw earlier can become a part of the natural ventilation strategy, where it can induce stack or buoyancy and be the outlet of natural ventilation scheme. We also spoke about night flush earlier. So we knew that if we charge this building at night, the thermal mass at night, it helps significantly increase the hours and people will be comfortable. So sometimes that can be done completely passively, but even if that cannot be for reasons that there is not enough wind or not enough pressure differential, we knew that we were going to use our air handlers, the dedicated outside air systems, to night flush this building to charge the thermal mass. From a systems perspective, of course, energy recovery was a no-brainer. We were going to make sure that we are not losing any ounce of energy through exhaust air. And then, of course, wherever we needed overhead versus wherever we needed displacement ventilation, based on the program, based on where we can achieve stratification, we were going to distribute our air systems accordingly. The next step that comes is, now that we have figured out what we want to do with air, how are we picking up the loads? And that's where you get into decoupled systems. So now we want to completely independently isolate the sensible loads from the ventilation requirement, because that's the most effective way of doing it. We also spoke about the radiant field around people. So we're not just relying on air systems to meet comfort. We want to make sure that we supply as little air as needed from a pressure perspective. And if I had not mentioned this, I should mention this is ASHRAE. So they are, of course, designing everything to 30% higher outside air rates than what standard 62 requires. So that all that outside air that we need, we are designing to, but from a sensible load perspective, from a comfort perspective, we want to make sure we deliver that from hydronic systems or hydronic terminal units such as chill beams or radiant ceiling panels or radiant stairs or something to that. So what that does is it starts making you think about two separate systems. One is the DOS, or the dedicated outside air system, that takes care of energy recovery from exhaust, at meeting your ventilation occupant health requirements, and then a completely different hydronic terminal unit system that sends cold water or warm water so that your radiant field changes and that it achieves comfort with minimal reliance on energy efficient or energy using systems, which also brings in a whole new plant equation now, because now you're not just cooling air from packaged systems, which is possible earlier, but now you need a plant that can generate chill water and hot water. This is going to be an all-electric building, so we're relying on heat pumps. Now, again, with heat pumps, you can have air source for heat rejection or water source. Of course, water source is way more effective. So we looked at different system configurations, and the final, of course, the ultimate frontier is if we can reject heat or use ground as a heat source for addition as well as a heat rejection source. So we evaluated that as well. But the idea is, think about systems incrementally. Think about what are the different things or items that you're trying to meet through those systems. And for each component, try to find the most efficient way to do that. So outside air is an energy recovery and demand control ventilation dedicated outside air system. Thermal comfort is as much radiant panels or radiant field that you can generate around air distribution, whether it needs to be overhead or underfloor. finally, where are your systems rejecting heat or adding heat from, and what's the most efficient way of doing that. When you think about it logically and sequentially from a systems perspective, everything starts to make sense. So this is where we ended up. After the envelope configuration, we were at 19, so slightly above the 17 target that we needed to be. And based on the system, if we simply did an all-air system without any radiant panels, but just efficient air distribution, energy recovery, demand control, ventilation, all the good things, we just about hit the target that we wanted to hit for ourselves. If we move to decoupled systems or hydronic systems, we save another EUI, and we get in the territory where we can now start generating everything comfortably, I would say, from the roof that we think we will consume. So that's almost the entire story of the project design. At the very end, the only thing I would want to add is, because we always, as engineers and as designers, you always want to keep a safety factor in everything that we do, even though our analysis is suggesting that P will generate 17 and we will offset 16. That still makes you queasy, that still makes you uncomfortable, because things can go wrong and PV might generate less and building might consume more. So we, as a last effort, we wanted to make sure we've maximized our potential for generation. We looked at certain other areas that we can include PV, maximize the efficiency of where the modules are oriented and how they are placed, because now we have a better skylight configuration. Now we have a better understanding of where the HVAC equipment will go on the roof. We consolidated it to one point so that we have more area available for renewable energy, and we increased our generation potential from what was 17 at the beginning when we first time we did the climate analysis to about 19 now. So to wrap up this whole process, towards the very end, we basically designed a project which could have been 36 EUI down to about 16 EUI, and we want to make sure that we have at least a 20% safety factor between what we are going to consume and what we are going to generate. So we increased our PV use to about 19 EUI. And that's where we are at right now. I should mention the project is in construction documents. I think we are very close to wrapping up the CD. So this is what the final design of the project is. The project will get into construction administration phase very soon, and hopefully this is what the building that ends up getting designed will be. We will see how the performance is once it's done, but that's where we are. So if you have not seen this rendering below, and there are a couple of things to take away from it, and this is where we will open it for questions, but I want to just say this. But this is what the building looked like, the image on the top. This is what the rendering, one of the more recent renderings that I've seen for the project are. Should clarify and mention and say that this is not a very glamorous project, because this was never meant to be. This is not flashy. This is not a sales headquarters. This is an headquarters of ASHRAE, and it's a replicable project, which means the interventions were left to be very minimal. The windows are punched and small. The atrium is done the way it's supposed to be, but nothing that did not need to be touched has been touched. And if the project can hit net zero with minimal cost investments, and if it can generate all the energy just from its roof that it consumes, and if it can achieve the comfort, both visual and thermal, that we've designed it to be, it'll be a super awesome story. That's where I'll leave it, and that's where we will open it for questions.
Thank you so much, Shreshth. You made it sound so easy, but I'm sure it had its own journey. And so just for reference to our listeners, 17 kBTU per square feet is about 49.8, like about 50 kilowatt hours per square meter. That's the kind of energy footprint this building has to get to net zero in a very cost-effective way, and in a method that is replicable and scalable. So without further ado, there are a lot of questions coming in, and I'll start taking them. All right, so the first question: there was a nearly 30% reduction in the plug loads compared to the baseline. How was that achieved?
I am going to start my camera right now so that people can see me talk and they know that I'm not, I am hopefully making sense. So yes, the plug load reduction was, as I showed in that graph and spoke about it, was strictly driven by ASHRAE's own project requirements. So every project here issues an OPR document, which is the owner's project requirements, where they establish criteria for themselves and for the design team. To put things in numbers, ASHRAE dictated that the plug load density for the project will not be over 0.5 watts per square foot for the entire building. We've done those kinds of projects in the past. We know that it is possible. ASHRAE most certainly knows that it is possible. So yes, it's slightly beyond the regular design process, but based on the equipment that you select, which means your computers and your microwaves and your printers and everything else in the building, we know that it is possible to design projects to hit that level of energy performance. Now, conventional plug loads, if anybody who's done energy models, they have baseline assumptions for what the equipment power densities should be and what the industry standard numbers for equipment power densities are. That reduction that you saw was strictly based on ASHRAE had developed a criteria or defined a criteria for themselves. The other piece in that graph that you saw was also lighting. It was not just plug. So again, ASHRAE has a criteria that the lighting power densities would be defined to a certain threshold. I think it was also 0.5 watts per square foot, and that 75% of the floor plate would be daylight or would get useful daylight illuminance. So those were the two things that ended up achieving that 30% reduction that you saw at the very beginning of the project.
That's a big one. 0.5 watts per square feet is really something for plug loads. Okay, next question. What features of the original building are being retained?
You mean besides the form, which we cannot do anything about, and the orientation? And like I said, we are changing the windows, but we are still keeping the modularity of the existing precast panels because we don't want to rip everything up because of the embodied energy that goes in there. The idea is to use it as a structure that we are trying to house ourselves in. So we are opening the roof with skylights, we are covering the roof of the atrium, we are changing the windows, we are reducing the size of the windows. But besides that, the whole building is exactly what it is. We are adding insulation, of course, but we are not throwing away anything. We are not generating any construction waste that does not need to be generated. We are trying to keep all the embodied energy within the building without disturbing it at all.
Right. Next question. Can you elaborate on the impact of nighttime ventilation?
Absolutely. So, sorry, go ahead.
Considering that the office has a minimal occupancy.
Right. So I don't know if I understand the question completely and as to why the occupancy of office is important, but the whole point here is that if you night flush your building because of the diurnal swing, if the nights are cooler, you charge your thermal mass. All the concrete slabs that are inside the building, if you make sure that air is blown over them, and we're using ceiling fans. I should have mentioned this earlier. You probably noticed this in the sketches. The ceiling fans that we have proposed are all reverse flow, which means they can blow air down and they can blow air up. The idea is during the night time, you run those fans in the reverse direction so that the cold air that can come in through the windows or through the economizer operation can be pushed up to the slab. The slab charges, and when people start coming in during the day, the radiant field is very different from what it could have been if the building was completely sealed. Now that you have a cooler radiant, talking about the summers, cooler radiant temperature, which means the thermostat or the air system or even the radiant systems have to do a lot less work. Only after that thermal mass has managed to absorb enough of the internal gains during the course of first few hours is when the radiant system needs to start meeting up for the rise in temperature. So the number of hours when you don't need to rely on systems once the office starts getting occupied increases significantly. You can meet the comfort criteria completely passively for a lot more hours if you manage to recharge your thermal mass at night. If I understood the question correctly, I hope it made sense.
Yes, I think that also answered the question on bidirectional fan, so I'm not taking that now. You've already
Okay.
talked about it. Next question. The surrogate model must have helped you select the best possible option, but the final
Right.
option or the output, was it based on the EUI or cost?
The cost, I think in all projects and all the projects that we work on, yes, we have a very motivated client who wants to do the right thing. I think ASHRAE is more aware and more driven by trying to hit an EUI target than anybody else. But I've yet to work on a project where cost was not a criteria, where you could do anything that you wanted to do. So, and that became way more important for this specific project, as I mentioned earlier, because this has to be replicable. Replicable from the perspective of how much money one needs to spend to hit a net zero energy performance target. So it's not just about how much money the client is spending for this specific project. It's about making a case that you don't need to spend a lot of money to be able to hit this level of performance. So everything was driven by cost, is still being driven by cost. Everything gets costed, we've gone through multiple VE processes, but what I showed you is what still managed to stick to the project. So Deepa, like you mentioned earlier, of course, it has been a very tedious project. We've done a lot of work on it. The story that I presented today seems straightforward because I picked the final decision at every step rather than going through the weeds of all the different options that we studied and what made sense. But absolutely, not just EUI. EUI is important, but cost drove all factors, all decisions.
Oh, interesting. Next question. What is the software used for the PV analysis?
So if you've done PV analysis before, you know that it's not rocket science. All that you need to understand is how much solar radiation falls on a surface that you're trying to evaluate, the generation potential. Everything else is just logical. The graphics that you saw, the analysis that you saw on this presentation, it was all done using radiance, which sounds strange because radiance is typically thought of as a daylighting software, but the idea is solar radiation because we want to consider self-shading impacts and context in trees and everything else. We have the entire geometry built into a 3D model already. We just take that model into a radiance analysis, run solar radiation analysis on it, and see that every surface where we're trying to implement PV or incorporate photovoltaics on, what the received solar radiation is. And then everything else follows from there because we know our module configuration, we know what the exposed cell area would be, we know what the thermal degradation factors are or what the efficiency curves are based on different incident angles and temperatures and all the good things, and we apply it from there. But this is all done, this is not done from a packaged PV calculation tool. This is done strictly from first principles where we want to make sure we've accounted for every loss factor or self-shading factor or potential radiation from all surfaces as accurately as we can.
Okay. Is there demand control ventilation in the open?
Absolutely. Yes. Yeah, I think nobody should ever design a project without demand. Why would you? I mean, it's just a CO2 sensor and a control. If you know that you can have varied occupancy and if you know that there might be times when conference rooms, for instance, are not going to be occupied, why would you be spending outside it in those spaces? So yes, that's a no-brainer.
Okay. Next question. Since the client was already motivated, was there any challenge convincing the client for any particular strategy?
No, it's always the cost and the EUI question, right? It's not the client they want their projects to be at the forefront of innovation. The convincing about a strategy is not at all a challenge. They would do anything that makes sense for the project. The challenge is to do that within a cost constraint that we've set for ourselves. So it was never about convincing the clients to pick a strategy. It was always about making sure that the strategy is cost effective.
Great. Next question. How reliable are surrogate modeling values?
Sorry, could you repeat that? I missed that part.
Yes. How reliable are the surrogate modeling outputs?
It doesn't matter. Surrogate modeling was I should not say it doesn't matter. Of course it does, because we're taking decisions based on that. But surrogate modeling, as you saw, was at the very beginning of the project. We used mathematical or statistical tools to narrow down the field of what we are trying to start with. But I did not mention surrogate modeling throughout the entire design process. Once we sat on the drawing table and once we start doing the actual design, we relied on actual engineering models to come up with what makes the most sense. Now that said, surrogate models, absolutely, they have to be reliable. I mean, if you know what you're doing, and if you understand your statistics, and if you have some idea of what the results should be, you can identify that the results make sense or don't make sense. Things like these, when you have no control over, if you end up in a black box, can go very wrong very fast. Anybody who's done any analysis knows that when you start dealing with black boxes, things can go very wrong. But if you know what you're doing, you can get reliable results. It can point you in the right direction, and that's the whole point of early stage analysis is hone down or narrow down on your choices, pick a few options that you want to evaluate in detail, and then of course everything is from there we did using engineering models.
Well said, and that was the last question for the session today, and I thank you so much. With this, we come to the end of the session. I thank you very much for your time, for sharing your expertise, and sharing everything in so much detail with us about this project. Before we wrap up for the day, I have a few more announcements to make and things to share. Next week, we have a webinar on Sierra E-Facility. It's a smart, high-performing building located in Coimbatore and has interesting things. After that, we have a presentation on the NETZERO energy building by design, which is a design school in National University Singapore, and that's also interesting to see how they've designed this building ground up in a tropical climate. We also have 2 net zero energy building tours scheduled, one on 14 September, the office building in Noida. It's a high performance climate responsive building designed by Ashok Lal, and the Infosys campus at Hyderabad on 28 September, which also has a state-of-the-art solar plant functioning on their campus that makes the campus net zero. And you must have already, if you don't know yet, we have a lot of short online courses on various topics surrounding sustainability, net zero, high performance building design. You can start taking the daylighting course if you haven't yet explored any of our courses yet. This is a good start. The coupon code is there in your chat box. If not, you can use this code to take the course for free. You can take these courses online on demand from any of your mobile devices. They are interactive video courses, which is about 30 minutes to an hour. And if you haven't yet subscribed to our monthly newsletter, please do so now. The NZE Times will reach your inbox every month with all the initiatives that we are already doing about the webinars, tours, the courses, events, etc. So do sign up today on our website and connect with us on social media. And with that, I thank you, each one of you, for attending this webinar, taking out time from your Friday evening to be part of this webinar and learn something new. Thank you very much, and I will see you next week.